Okay, so maybe I can get started. It's almost 11:30 now. Yeah, so during the last lecture, we took a look at the early universe, and we first figured out that yes, because the scale factor is actually decreasing as a function of time, the universe is expected to be smaller and hotter. And so we tried to figure out what do the standard model of particles in the standard model of particle physics, how do they behave, and what would be happening to them, right? So in particular, we learned about the redshift of matter radiation equality, and then we also figured out the equations for the number density, the energy density and the pressure, as well as the entropy for these different particles, which will be in thermal equilibrium with the radiation at that epoch, right? So using many of these equations, and we had to go through some complicated details and mathematics, but we went through a couple of important phases and things that happen in the universe. In particular, we figured out that if you, like, there are these relativistic and non-relativistic limits for the number densities, right? And if the particles remain in thermal equilibrium, even long after they become non-relativistic, then there is a exponential suppression of their abundance due to this annihilation and annihilation processes taking over and being much more favored than the creation processes that happen with these photons, right? We also looked at a couple of different epochs. So, for example, we looked at the thermal history of the universe and when each of these annihilations happen of the different standard model particles. We also took a look, especially at the neutrino decoupling epoch. What happens to the neutrinos? At what point do they decouple? And after that, in the end, I briefly talked about the formation of heavy elements in the universe, right? So not just the protons, but the protons and the neutrons, they fuse to form deuterium, and then it leads to the formation of helium. Okay, so those were the things that we talked about last time. So there was the neutrino decoupling epoch and the neutrino background. And also this formation of heavy nuclei. So that's where basically I had stopped last time. So we are trying to figure out what is the abundance of helium that we should observe, the primordial abundance of helium. And because this is an observable, this actually puts constraints on many of the physics that went into predicting this particular primordial abundance. Okay? So it turns out that all these processes, these happen in the first few minutes after the Big Bang, right? And so these kind of processes are very, very quick. Okay? So you form elements up to like lithium, maybe trace amounts of beryllium, but that's about it, right? And so to form any of the heavier elements, you need some other processes, some other astrophysical processes that happen later on, rather than something happening in the primordial universe, like in the first few minutes. Okay? So those often happen, like the formation of carbon, nitrogen, oxygen, and so on. They happen later on in the guts of stars, right? So when stars have their nuclear reactions in order to convert hydrogen to helium, later on that helium starts to burn and then converts into the higher elements, right? So this is how you form the higher elements. But in the primordial Big Bang nucleosynthesis, you form basically hydrogen, helium, trace amounts of lithium, so on. Okay, not any of the bigger elements. Okay, so this is what we learned until yesterday. So today, what we are going to do, this was about the first 3 minutes or so after the Big Bang. So now we are going to see what happens afterwards, right? So after these epochs, what you have left is the electrons and the protons and the photons, right? They are in thermal equilibrium again with each other. So the electrons are trying to combine with the protons to form bound hydrogen atoms, right? Neutral hydrogen atoms. But because the photons are so energetic, the photons, they come and they hit the electron. and then they kick out the electron out of the orbit of the proton, right? So you cannot form bound atoms for a long, long time, because as soon as the electrons and the protons, they combine, then there is some other photon which will come and hit them, okay? So because of this process, the universe is extremely opaque. And the reason for it is, if the photon is trying to travel in the universe, as soon as it is traveling a little bit, it encounters a neutral hydrogen atom, and so it just kicks out that electron, right? And so then it scatters, okay? It's like you are in the middle of a huge fog, right? That you cannot see um, um, see what is happening out to a certain distance just because of this. Okay? So this particular reactions, the electrons and protons combining to then form a neutral hydrogen atom plus a photon, this particular process is going on in the universe, right? So what you can do is you can ask the question, okay, what is the relative abundances, relative number density ratios of the protons and the electrons to the hydrogen atom? So these protons and electrons are on the left-hand side, hydrogen atom is on the right-hand side, right? And so, of course, the relative ratios of these quantities, they should be related to the temperature of the photons, right? And so that's what you see here on the right-hand side. There is a temperature which is there on the right-hand side. This basically is the ISSAA ionization equation. Again, you must have studied it during the stellar structure lectures, right? And so what you're seeing is basically these relative abundances. They are related to these temperatures. And then there is also this exponential factor minus chi by kBt. So this chi is nothing but the energy difference between these, or the binding energy of the hydrogen atom. Okay, so it's about 13.6 electron volts, right? So that is what goes on in this exponential factor. So if you just look at this equation, you would think that, okay, the photons will not remain energetic enough once the temperature drops down to something like, or kBt drops down to something like 13.6 electron volts. Okay, so this temperature is of the order of 10 to the 5 Kelvin or so, right? Because after that, there's an exponential suppression, and so you will think that, okay, these NPs and NEs, they will start to get bound to form these hydrogen atoms, right? But it turns out that this doesn't really happen, okay? And let me try to tell you the reason why this particular process doesn't happen at 10 to the 5 Kelvin. It requires temperatures which are even lower than 10 to the 5. Okay? So what we are going to do is we are going to transform this equation and use a quantity called the baryon number, right? So the baryon number is nothing but the number of protons plus the number of hydrogen atoms. If you add them together, this will give you the baryon number or baryon number density, right? Okay. So then, in order to cast this ionization equation, what you can do is you can define a quantity called X, which tells you what is the relative number density of the electrons to the baryon density. Okay, and so if you use this equation, you can transform this ionization equation to something which is written at the bottom of this screen, right? So basically, you will get an extra NB, which comes in the denominator here, because there are NP times NE, which is in the numerator of this equation, and NH, which is on the denominator. So you can try to convert the NP and NE in terms of the baryon number density. You'll get all these excess, and the NH, you'll get a 1 minus X times NB. So one of the NBs will cancel from the left-hand side. The remaining one you are taking to the denominator. Okay. Okay, so you have a baryon number density, which is at the bottom here. And then there is a temperature, right? So the temperature you can always relate to the number density of photons, which are there, right? And so what next I'm going to do is I'm going to use a quantity called a baryon photon ratio, okay, in order to substitute this NP and make it into N gamma, which is the number density of photons, okay? So this NB that was there in the denominator, I'm just writing it as eta times N gamma. Okay? So N gamma is the number density of photons and eta is the baryon photon ratio. So now that we have this in this particular form, we can then substitute the number density of photons in terms of their temperature. So that goes basically as P cube, right? So that is what is done in the next step here, right? And so once you do all of this, then you get the bottom equation, which is written. Right? So you see that there is something like t to the minus 3 by 2 exponential minus chi by kBt. But then there is this eta factor which is present here. Right? So if this eta was of order unity, then you would see that, okay, this x will be very, very close to, right. So x, which is the number density of electrons compared to number density of baryons, that will be very, very small when the temperature is of the order of 13.6 electron volts. But because of this eta factor, the temperature has to be even smaller in order for this x to be small. Okay. So the reason for this is that this eta, you can measure the value of eta today, which is nothing but the number density of baryons to the number density of photons, right? So this number is of the order of 10 to the minus 9. So because this is 10 to the minus 9, this can, and it is in the denominator, so it goes to the numerator, it will become 10 to the 9, right? So this extreme high factor, it counterbalances this exponential, which you see here in this right-hand side, okay? And that's why for having a x which is small, which means that the number of free electrons to be small, so that all of these things are bound into hydrogen atom, you need the temperature to be even lower than 13.6 electrons. Okay? So the temperature has to be something of the order of 3000 Kelvin instead of the 10 to the 5 Kelvin that you would get if you just assume 13.6 electron volts. Okay? So the temperatures fall down to those levels roughly 380,000 years after the Big Bang, right? So it's a long, long period in between that has to be gone before you start to see these neutral hydrogen atoms forming and staying neutral, okay? So again, the intuitive way to understand this, the physical picture that is going on is, remember, you have photons, right? And these photons have basically a Planck distribution, right? And so what you need is a sufficient number of photons in the energetic tail of this Planck distribution to be able to kick out the electrons from the hydrogen atom, right? So that can happen until the temperature is 3000 Kelvin, okay? Just because of the size, the numbers of the photons that you have, right? Because it is so large compared to the number of baryons that you have, you can have a small tail in the Planck distribution and still that can be energetic enough to ionize all the hydrogen atoms that you have, okay? And that's the reason why the universe doesn't get neutral, okay? So it doesn't form these neutral hydrogen atoms until the temperature drops down to 3000 Kelvin, okay? So that's the physical picture behind this, okay? Okay, good. So what happens after that, right? So after that, the photons are now ready to free stream, right? Because there is nothing which is stopping them. Even if they encounter some hydrogen atoms, they don't have enough energy to displace, and so they just go, they basically just keep on free stream, right? And so this particular photons that got released at the end of that foggy epoch, right? Those are the things that you can still observe today, okay? And this particular aspect was very well known, so it was predicted much before it was actually observed. Okay, so it was predicted in a paper by Alpha, Beta, and Gamow, right? And they had predicted that there should be this particular background which should be detectable. In the 1960s, there was a group in Princeton which was trying to build these antennas, radio antennas, because it was expected that the temperature will be of the order of a few Kelvin. And so they were building these giant radio antennas in order to detect the signal. But they were beat to it, okay? And they were beat to it by this group of guys, Arno Penzias and Robert Wilson. What they were trying to do is they were trying to establish a transatlantic communication, okay? And so they were building these giant radio antennas. And what they found was that there was an irreducible source of noise, which was always observed, whatever they did. Okay, they cleaned up their antennas, They did a lot of different engineering things in order to reduce this noise, but they were never able to get this out. Okay, so it was impossible to eliminate. Whichever time of the day they observed, they saw this particular noise, and it was uniform in direction and time. So whether they looked in this direction, that direction, it didn't matter. They always saw this. When they started to talk with their Princeton colleagues, that's when they realized that they had indeed discovered this cosmic background of photons, which was coming from the very, very early epochs. Okay? And for this, they also received a Nobel Prize. Right? So the temperature of this background corresponded to about 3 Kelvin. Okay? So 2.7 Kelvin or so. That's what they had discovered. Okay? So after that was discovered, there was a big rush to make sure that this actually is a black body, right? Because we expect if the photons are in thermal equilibrium that it will give a black body spectrum, right? And so there was a special satellite which was built. It's called the COBE mission, the Cosmic Background Explorer mission. And so it went into space and it measured the direction of the CMB. It actually measured the spectrum of the CMB, and it also measured the temperature of this emission in all different directions. Okay? So the first thing that it found is that, yes, indeed, the spectrum is black body. Okay? And so what you're seeing on the left-hand side is the black body spectrum, which was observed by COBE. And then you will ask, okay, how can this be a measurement? Because you are not showing any error bars. The reason why I'm not showing the error bars here, or why you cannot see the error bars, is because the error bars are smaller than the fraction of the thickness of this line. Okay. And so it's as good a black body as you can get, right, basically. So it's the best naturally observed black body spectrum that has been found, right? And so this is the relic photon background from the universe's hot and dense past. So that's what COBE was able to figure out. It was able to measure the spectrum very, very accurately. And this is what it found. But then there's this curiosity, right? If everything is exactly the same in each and every direction, then it means that the universe is extremely homogeneous, right? And if the universe is extremely homogeneous, then it would be actually a big problem, right? The reason for that problem would be that you need to form structures like the galaxies that we see, right? Or even things like us, right? So you should be able to find fluctuations within this background. Okay. Now, there were some naive expectations even before COBE flew as to what the level of these fluctuations should be. Okay. And the expectation was that these fluctuations should roughly be of the order of 10 to the minus 3. Okay. So the fluctuation should be of order like 1 in 10 to the 3 or 10 to the minus 3. That's the relative density temperature fluctuations that you should have seen in order to form the structures that you see today. Okay? And so there were many, many missions which were trying hard to detect this from the ground, but they were failing miserably. Okay? So COBE tried to put a nail in the coffin into the measurements of these initial density fluctuations. Okay, so this is what it found, right? So the first thing was that it found that there was an extremely isotropic emission, right? So the temperature of the CMB was 2.73 Kelvin, no matter where they looked, right? So this is basically the first topmost panel that you are seeing. Okay. So what that particular figure is doing is taking each and every direction in the sky and mapping it to one of the points in this ellipse. Okay, so this is a full sky map. It's some kind of projection where you take a particular theta phi and then put it onto a particular pixel here. Okay. So it's basically just the same like you take a sphere, which is the Earth, and then you put it on some kind of flat projection, right? So that it is easier to visualize on a piece of paper. So that's exactly what is done. So the color scale is telling you what is the temperature, right? And what you see is that it is extremely uniform at the level of 2.728 Kelvin, right? At that particular temperature, everything looks extremely uniform. So then they said, okay, let's remove out this uniform temperature. So instead of looking at the temperature, let's look at T minus T average. So when they look at T minus T average, they are on average supposed to get 0, right? Just because you are subtracting out the average. If you average over all the pixels, you should get 0. But you can also start to see some fluctuations. So you can dial up the contrast to see whether there are any fluctuations left over. So this is now the map of delta T, and the contrast is increased so that you can see things at the level of millikelvin. So when you look at it in the millikelvin level, this map of delta T, that's when you first start to see some differences, some inhomogeneities. So you start to see a kind of a dipole pattern where one of the sides is a little bit hotter, other side is a little bit cooler, right? But of the order of a few millikelvin. Okay, remember this was Kelvin, this is millikelvin. So of the order of 10 to the minus 3 kelvins, right? Now this dipole occurs because our own galaxy is not at rest with respect to the CMB. Remember in the previous classes, I've talked about these peculiar velocities, right? So our galaxy has a non-zero peculiar velocity. And so it is not a fundamental observer. And because it is not a fundamental observer, what will happen is towards the direction of its motion, it will see the CMB photons coming from that particular direction to be a little bit hotter compared to from the direction behind. Okay? And so this is the reason for this particular dipole pattern. So it's a pattern that can be removed, right? So you can remove out this first order dipole, which happens just because of our motion with respect to the CMB. So once you remove that out, then again, if you look at millikelvin level, you don't see anything. So you have to dial it down to tens of microkelvin contrast. That's when you start to see fluctuations. So these are the fluctuations that you see in the cosmic microwave background. You have to tune it down. You have to tune your contrast down to tens of microkelvin. Okay. So these fluctuations, they were observed as 1 in 10 to the 5 rather than 1 in 10 to the 3. Okay, and I will try to explain why this is also important as we go on further in this class. Okay, but the presence of these fluctuations was extremely important. Okay, because these fluctuations then tell us that the universe is not really homogeneous. It has some inhomogeneities, but at a very, very small level. Okay? And it is these inhomogeneities that act as the seeds for all the structure that you see in the universe today. Okay? So observing those was also very, very important. The reason why the universe is assumed to be isotropic is because of the CMB, this first particular map that you see, right? It's 2.728 Kelvin in almost all directions, and the fluctuations are so tiny. That's one of the biggest observational proof that we have that the universe is isotropic around us. Okay? Of course, we have to account for the fact that you're removing these peculiar motions of the galaxies, right? Remember, the universe is not isotropic from each and every frame that you can think about, right? There's a special frame of these fundamental observers with respect to which the CMB appears isotropic, and then everything is also homogeneous as well. Right? That comes from the galaxy observations. Okay, so now this particular discovery of fluctuations that again earned the Nobel Prize for John Mather and George Smoot, right? So that is again a Nobel Prize winning thing. It was the second Nobel Prize which was obtained for discoveries in the CMB, right? Now the question is, why are these fluctuations important? Where do they come from, right? And it turns out that the physics of these fluctuations is extremely simple, okay? And so that's what we will try to understand. We'll try to understand what is it that we see in this particular map. Before I go there, I wanted to show you the progress that has been made in the field of the cosmic microwave background from the first time the fluctuations were discovered by the COBE collaboration, which is seen here, to the Planck collaboration in 2015, which produced this particular exquisite pattern, right, that you see of the temperature fluctuations, right? So you can see that the patterns are very, very similar if you look at it on the larger scales. So here you see like a bluish map. This is the pattern here. Then there's a hotter pattern here, a hotter pattern here, etc. Right? So the large scale features you could see already in the COBE map. What Planck did is to map it out at a much higher resolution. Okay, so that's great. So this is the progress that has been made, but this progress has allowed us to now understand what this particular pattern tells you about. In particular, there is one particular scale that jumps out at you, right? So there is a particular size of the hot spot and the cold spot regions, right? So this is about a degree scale that pops out. Okay. So what is the relevance of this particular scale? That is what we are going to try to understand next. Okay. So in order to statistically quantify what these fluctuations are telling you, what you have to do is define something called a temperature correlation function. Okay. What this temperature correlation function does is very, very simple, right? So you take one point in the Planck map or the CMB map, right? And then you take another point which is separated by an angle theta. Okay. You take the delta t value at the first location, delta t value at the second location, you multiply them. Okay. And then you take an average over all different positions of the first and the second point, such with the condition that these 2 points are always separated by an angle theta with respect to us. Okay. So that particular quantity is called a correlation function because you are taking the delta t value at one location, delta t value at another location, which is separated by an angle theta. So that's the correlation function. But the physics of the CMB, it is all related to the propagation of sound waves in the early universe, right? Remember, these are density fluctuations, right? And what these density fluctuations are happening in, they're happening in the baryon photon fluid, right? So there are electrons, protons, and photons. They are tightly coupled with each other, right? The sound speed within this particular medium is nothing but c by square root of 3, right? So this particular factor, c by square root of 3, this is coming from the equation of state that you will have. If everything is relativistic, then P is equal to Cs square, or P is equal to C square by 3 times rho, right? That is the equation of state that we had worked out. And so when you look at dP by d rho, you will get basically the sound speed square, which is nothing but C by 3, right? And if it is C by 3, which is sound speed square, then the sound speed is C by square root of 3, roughly. Okay, this of course applies when everything is relativistic. As time progresses, these relativistic equations will acquire some kind of corrections, right? So just a rule of thumb, it will be roughly C by square root, right? Okay. So because these are sound waves, it becomes easier if you analyze these things in Fourier space, right? And you have to decompose these correlation functions in terms of the values called CL. So you can decompose it in terms of spherical harmonics. So these coefficients CL, they go in front of the spherical harmonics. So this is nothing but trying to calculate the statistical properties, the correlation functions, but now in the spherical harmonic space. Okay. So we will be looking at what these CLs are going to tell you. So this particular thing is nothing but trying to analyze the Fourier modes, okay, the Fourier components. Okay. So that's what we are going to do. Okay. So let's try to understand where these fluctuations are coming from, right? And so what you have to think about is that in the very, very initial stages, there are some initial density fluctuations. And then what we are looking at are how these density fluctuations have evolved from the very, very initial stages to the CMB, right? To the time when CMB was released. That's what we have to do, right? And so the reason why these initial fluctuations exist, that is because of something that happened in the very, very early universe. It is an epoch called inflation, where the universe undergoes an exponential expansion. Okay, this particular aspect you will study in your structure formation lectures. Okay, so I'm not going to go into the details of it, but remember what inflation does is it takes tiny quantum fluctuations which are present in the very early universe and it stretches them out to astronomical scales. Okay. These fluctuations, which were imprinted at the end of inflation, these fluctuations then grow, right? And these fluctuations are the ones which result in the fluctuations that you see in the CMP. Okay, so that's the part about it. Now we want to understand how these fluctuations play a role into what you see in the CMP. Okay. So let's look at some of these fluctuations here. So what you are seeing here is a particular scale in the fluctuations. Okay, so a particular wavelength of fluctuations, that's what you are seeing. Okay, so any of these initial density fluctuations which were set at inflation, you can expand them out in Fourier modes. So what you are seeing is one of these Fourier modes. Okay, so this particular picture that you see on the left hand side, that is the fluctuation at inflation. Okay, so what you are seeing here are the potential wells which are formed by some density perturbations, and these density fluctuations are in some matter component. Okay, and this particular matter component is going to be dark matter which does not interact with light. Okay, and we'll get back to why it needs to be dark matter, etc., etc. So let's go slowly with that. Okay, but this particular fluctuation, that's what you're seeing. Okay, and so the dark matter fluctuation is here. There is a potential well here, which means that there's a gravitational potential well here, and then there are baryons which are here, which are shown as these tiny blue balls. Okay. Now, these tiny blue balls, they are in equilibrium with the photons, and so they have a temperature. So you will see that the temperature is hotter here, colder here, hotter here, colder here, hotter here, etc. Okay. Now, as time progresses, what will happen is that the hot spots, right, because you have these sound waves, the hot spots will become cold and the cold spots will become hot. It's just because there is a wave traveling, right? There's this sound wave traveling. And so the hot spots become cold, cold spots become hot. That's it, right? And so when you go from inflation to recombination, let's think about a particular Fourier mode, right? A particular Fourier mode where the distance between these two places is such that it is exactly equal to the sound speed times the time to recombination. Okay. So if that is the case, then what will happen is this hot, this thing which was hot, it will become cold, and this thing which was cold, it will become hot, right? And so the temperature fluctuations will have a contrast which is the largest on this particular scale. Okay, so the Fourier scale, right, or the Fourier wavelength, where the wavelength of this mode is exactly equal to the sound speed times the time to recombination, that particular mode will have enhanced fluctuations on the spot. Okay, so this is what gives rise to the cold spot and to the size, typical size of the cold spot and the hot spot. Okay, so the distance between this hot and the cold on average should be roughly CS, which is the sound speed, times the time to recombination. Okay, once we know these things, that gives us a physical scale that we can look at. Okay, so that's the first part. The second part is, depending upon how much dark matter you have compared to the baryonic matter, these wells would be larger or smaller, right? And if these wells are large, right, what will happen is, remember the sonic motion, right, which is this is hot and this is cold, and that's why the hotter things would like to go to the colder place, right? And so these particular baryons, they will go and try to be in this colder place, right? So what is happening is that gravity is assisting this motion in this particular case, right? And so depending upon how the dark matter is distributed and what is the fraction of dark matter to the baryons, it can cause the temperature fluctuations to be even larger or a little bit smaller, and so on. Okay, so this is the origin of the temperature fluctuations. It is nothing but something which is related to to the propagation of sound waves in the early universe. So let me show it to you in a little bit better manner, perhaps. Okay. So what you can think about is this first particular mode that I was talking about, right? This is the fundamental mode, where at inflation it was hot, right? And then on this axis is basically time, right? And so what you are seeing is that the hot region, it came down, became came to the same temperature, and then it became cold right at the time when the universe recombined. Okay. Now what you can do is you can look at this particular thing, which is on the time axis. Now you can just flip it on the horizontal axis, which makes it in the plane of the sky, right? So in the plane of the sky, what will happen at the point of recombination is this particular location will be cold now, right? But the other end in the plane of the sky, right, in this direction, it will be hot, right? And because the wavelength is perfectly matched to CS times the time to recombination, what you will see is enhanced fluctuations on those scales. Okay? So the first physics is basically related to having these sound waves go off in open pipes. Okay? The one end of the open pipe is at inflation, when initially someone struck the hammer, right, on a piano string, for example, and that's what started this sound wave. Okay, and the sound wave is now propagating, and you see the fundamental mode in terms of the largest inhomogeneous peaks that you see, or the largest hotspots or cold spots that you see in the CMB map. Okay, but just like any instrument, right? If you have a piano string and you hit the hammer on that string, it not only gives rise to the fundamental mode where the string is going just up and down, right? But it also can give rise to these overtones, right? That causes the rich sound of a piano, if you have ever heard this particular instrument, right? And so these overtones are also seen in the CMB. And so instead of just looking at the first fundamental mode, you can also look at the first overtone, where initially you will have a hot spot that becomes a cold spot, then it becomes a cold spot, then it becomes a hot spot again. So on smaller scales, you can again see more inhomogeneities, right? And so this will give rise to another temperature fluctuation enhancement at an angle which is some sort of an angular multiple of the first angle. Okay, so just like you have these standing waves in open pipes, then you can have a second overtone, a third overtone, etc. Okay? So the typical size of the CMB spots, that now acts as a standard ruler, and once you have a standard ruler, then you can measure the angular diameter distance to the epoch of the CMB. So this is something that has been done by using these CMB maps. Okay, and so what you're seeing here is this temperature deviation from average. It's nothing but this CL times this 2L plus 1 by 2 pi, this kind of factor. Okay, so this is in power spectrum space. So what you're seeing here is the angular frequency, and this is nothing but the inverse of the theta angle that I was talking about, right? When you are taking the correlation function. Okay? So these are small scales, these are large scales. Okay? So just naively thinking about what you are doing is you are taking the CMB map, you are averaging it over large scales, okay, and then calculating the variance of the temperature map that you get. When you average over large scales, this is what will be given here. When you average over small scales, this is what will be given on the right hand side of this graph. Okay, so what you see is this particular pattern where the temperature fluctuations have a variance which is the largest at a particular scale. Okay, and this particular scale is nothing but the fundamental mode that I was talking about. Okay, so this is the fundamental mode, and then you start to see these extra peaks. Okay, and these peaks also happen at these multiples. Okay, so this is telling you that it is the physics of the simple sound waves, sound wave propagation that I was talking about previously. Okay. Okay. So if you again take a piano and then plot a frequency histogram of the sound that you hear, you see something similar. Okay. So this is what helps us to say with a lot of confidence that there is a particular angular scale, there is a particular something that started the initial fluctuations, and then these fluctuations evolved because of the sound waves, right? And then that is what you see as the CMB map today. So at least the fluctuations evolved in terms of sound waves for the baryon photon fluid, and these fluctuations in the baryon photon fluid is what you see today. Okay. And those can be analyzed in terms of the physics of the sound waves. So that's the great part about this, right? So this is an observable. This has been observed to very, very high precision. So I will show you what the observations look like on the next slide. Okay. The other important thing that this particular kind of graph tells you is that the relative heights of these peaks, as I told you, they can tell you something about the amount of dark matter to the baryons. Okay, so the relative ratio of the dark matter and the baryon density, that can be learned from the relative heights of these peaks. Okay, the first and the second, first and the third peaks. These give you the ratios of the dark matter to the baryon density. So that again is something that can be easily observed or easily inferred by looking at these kind of observations. So let's look at the observations. This is the what you see from the Planck data from 2015. This is the data, right? And you see, I don't have to show you where the peaks are, right? I don't have to draw that red line at all. You can see the peaks even in the data itself, right? Because the error bars are so tiny, right? So you can see the first peak easily, second peak, third peak, fourth peak, fifth peak, sixth and seventh, maybe at a smaller significance, but you can definitely make them out, right? So all of these things, these kind of observations, they can allow you to then measure the angular diameter distance to the cosmic microwave background radiation, EP. It also allows you to measure the relative heights of these peaks and tell you what is the composition of the universe at recombination. So let's look at what that tells you. So this is the picture when the universe was about 380,000 years old. Now, we will come back to the upper panel later. Let's look at the lower panel. So at that point of time, when recombination happened, based on these relative heights of peaks and trying to fit to this particular temperature power spectrum that you see, we can deduce that 12% of the energy density at that point of time in the universe was composed of atoms that we understand, right? These baryons that are understood in terms of the standard model of particle physics. 15% of them were photons. So the baryons and photons roughly in the same kind of density proportion. There were neutrinos, about 10% of them. And then 63% of it was dark matter. Okay. So this was the combination that can explain the observed signals that you see. Okay. So that's the first thing. But then, because you can measure the angular diameter distance to the CMB, you can also try to figure out what is the geometry of the universe. This geometry of the universe is determined by dark matter and dark energy today, right? Because it's the whole distance, the integrated distance that you're looking at. So that particular measure also allows you to put a constraint on what the constituents of the universe should be today, right? And so you see that you need to have dark energy of the order of 70%, dark matter of the order of 26%, and the rest of the things are photons, right? Are atoms, right? So the standard model of particle physics, the particles that the standard model applies to, right? You will see that neutrinos have gone away because their energy density goes down as 10⁻⁴. Photons have also gone out. They are extremely tiny slivers here. It can be measured. It's a very small sliver. That's what is left. Okay. So the universe today, the homogeneous universe, can be described by these particular cosmological parameters. And we know what is the composition, what is the ratio between dark matter and atoms. That ratio stays constant. So if you take the ratio between this 12 and 63, 4.9 and 26.8, it will be roughly, I think it's like 85% of the matter is in this particular dark matter set. Okay? So that's about CMB that I'm going to talk about. So in the last 15 minutes, I want to quickly go through the evidence for dark matter. So I told you the evidence for dark matter can be also seen in the CMB. In fact, the most precise measurements of how much dark matter is there in the universe, they come from the CMB. But the fact that there is dark matter was known even before. In the 1930s, Fritz Zwicky, what he had done is he had measured the velocity dispersion of these tiny, tiny satellite galaxies in galaxy clusters. Okay? So what he did is just measure the relative velocities of these galaxies, these tiny yellow galaxies that you see around the center of this cluster. Okay? And so when you do that, you can measure a velocity dispersion for these satellite galaxies. And when you measure the velocity dispersion, and if you know the distance to this cluster, remember at that time, Hubble had perfected the art of measuring the distances to these galaxy clusters. Then Zwicky was able to figure out what is the dynamical mass which needs to be contained in these clusters in order for these satellite galaxies to stay bound, even though they have such a high velocity dispersion. So when he measured that, he found out that the amount of mass that is required in order to keep this system bound is much larger than the amount of mass that you see in terms of the visible matter. And so that particular remaining mass was termed a dunkle materie, or something which is like unseen matter or dark matter, which is required to be holding these clusters of galaxies. Okay, so the baryon density, we cannot explain the large velocities that the satellite galaxies have in the cluster. So I'm not going to go into the details of dark matter at all. Unfortunately, this year, Varun Sahni cannot give a lecture on an introduction of dark matter, but I encourage you, I have put in the link on my slides for his lecture from 2020, last year, in the refresher course. So there is a link here. If you click to it, you can listen to his lecture. So please go through. In the 1930s, even though that evidence was found, that evidence was perfected and people started paying more and more attention to it. When Vera Rubin, she measured the rotation curves of gas around nearby galaxies. Okay, so when she measured that, she found that the rotation curves, they did not show a Keplerian decline of the circular velocity falling down as 1 over square root of r, where this is the distance from the center of the galaxy. So it's basically gas which is moving around the center of this galaxy. You're trying to measure the rotation velocity. Okay? So when you measure the circular velocity, if you want to know the mass which is inside, then it will roughly go as 1 over square root of r as you go further and further out from the galaxy, right? From the baryonic matter of galaxy. But instead, what she found is that the circular velocity curves were flattening. Okay. And so this flattened circular velocity curves, it was not found around one galaxy, but most of the spiral galaxy that she had observed. And that's when we knew that indeed there must be some mass which is increasing as a function of radius, but it is not something that we can see. Because if you look at galaxies, they are the densest at the center and then they fall off as you go further and further out. But there is mass which keeps on increasing as a function of radius instead. Okay. So that was the evidence for dark matter. Okay. But I'm going to tell you some other line of evidence for dark matter as well. And this is what is extremely important. Remember, I told you that the fluctuations that are present in the cosmic microwave background, in the baryons, right? They have to be they are observed to be of the order of 10 to the minus 5. But I told you that in order to form the structure that we see today, the galaxy clusters, for example, that we are seeing today, these fluctuations should have been of the order of 10 to the minus 3 at least, right? That's what people were trying to observe at that time. We saw that the fluctuations in the CMB are of the order of 10 to the minus 5. So what gives, right? So what gives is the following, right? that these temperature fluctuations are so small because the baryons, they were coupled with the photons until that point, right? Photons, remember, are relativistic, right? And so whenever these baryons are trying to fall into the potential wells and try to form a hotspot, the radiation pressure will try to drive them out, right? This is the reason why there are these fluctuations, right? And these fluctuations are extremely small because the baryons are still coupled with the photons. But there is something which is not coupled with the photons, and that is dark matter, right? And so dark matter has decoupled much earlier, right? And so if it has decoupled from the photons much earlier, now it can definitely start to make bigger and bigger potential wells, gravitational potential wells. And the fluctuations in dark matter, they can grow, even though the fluctuations in baryons are hindered because of their interactions with the photons. Okay, so if there are only baryons and photons in the universe, right, and we have seen the fluctuations in the cosmic microwave background, which are of the order of 10 to the minus 5, until today, you wouldn't have been able to form galaxy clusters. Okay. The only reason why you can form these galaxy clusters today is because there was some matter which was not coupling with the photons. Okay. If there was nothing like dark matter, you would not form the structures that we see. Okay. So that is another line of evidence for why dark matter should exist in the early universe. And the exact ratios of this dark matter density to the baryon density, these have signatures in the temperature power spectrum that I showed you before. Okay. Okay. So far I have talked about geometric probes, right? So you can measure the geometry of the universe by measuring the distances to objects, right? Either you can measure angular diameter distances, for which I gave you the example of the CMP, or you can measure luminosity distances like you saw here, which is shown by using supernova, right? So for example, there is a supernova which went off here, and you can measure its observed flux. Based on the observed flux, you can deduce what is the luminosity distance to this particular galaxy. So if you know the luminosity distance and the redshift of this galaxy, you can put it on a plot, the luminosity distance redshift plot, as you can see here, right? And you can vary these different models like omega matter 0.3, omega lambda 0.7, omega matter 0.3, omega lambda 0, etc., etc. And you can ask which of these models fits the luminosity distance redshift relation accurately, right? And the model which fits it accurately, that's the real model for the universe, right? Of course, there are many, many degeneracies. So it doesn't mean that you will get just one model. You will get a confidence region of what particular possibilities are okay, given the observations, right? So this is what is seen on the right-hand side. So this is omega lambda on the y-axis, omega matter on the x-axis, okay? And just by looking at these observational points, you can use my code, for example, to take the omega matter, omega lambda, and try to calculate these lines, right? And you can ask, does the observation support this particular model or not, right? And you can ask in the omega matter, omega lambda plane, which of these points are allowed, right? And what you're seeing here are the confidence regions, right? So at 68% confidence region, the supernovae data, this particular data that you are seeing here, they tell you that omega matter and omega lambda can only have this particular combination. Okay, that's what the data is telling us. Remember, I told you about the CMB. You can use the CMB, and especially that size of the spot, exactly at what angular scale the peak occurs, right? The first peak occurs. That tells you the angular diameter distance to the CMB. So you can work out which of these models, omega matter, omega lambda, which of this in this whole space is able to explain the observed CMB, right? And so there you see that this is this green line, which the CMB tells us, okay? So if you look closely, the green line is very roughly mirroring the line of a flat universe, okay, where omega matter plus omega lambda is roughly equal to 1. Okay. So that's why people say that the CMB actually tells us that the universe is flat. It's looking at that particular scale, and then based on that, it can figure out what is the angular diameter distance at that redshift, and so figure out what the geometry of the universe is, right? So it can tell you that it's roughly flat. Okay. So you take the CMB, you take the supernovae, we'll come to clusters later. So you take the CMB and the supernovae. So the CMB tells you that the universe can be here, right? Where omega matter is something like 1-ish, but then omega lambda is 0. CMB doesn't preclude that necessarily, just the geometric distance measurements, right? But supernovae tell you that it cannot be possible. Right? So you have to lie at the intersection of these curves, and that's the reason why we can get some sort of a concordance model from these kind of observations. Okay. Remember, now the CMB observations have gotten much better. This is from 2004, right? So by now things have gotten much tighter. Okay. So by themselves, CMB observations can give you some evidence for dark energy as well. Okay. So you will see, you can again see lectures of dark energy, which were given by Varun Sahni last year. If you want to learn more about dark energy, please go there. Okay. There is another thing that you can observe, which is called the Baryon acoustic oscillations. Okay. So this is nothing but the same physics of the CMB that I talked about before, right? But the fact that these baryons had some oscillations, right, in the power spectrum, that actually corresponds to a particular scale where you see a bump in the temperature fluctuations, okay? And these temperature fluctuations then also manifest as some sort of bumps in the correlation functions of galaxies that you can observe today, okay? So I'm not going to go into the details of this because I'm running short on time, but these baryon acoustic oscillations are basically oscillations or bumps that you can observe in the galaxy correlation functions. Okay, what exactly is again a correlation function? This you will learn in the structure formation class. Okay, so this particular bump was expected to be seen just from the fact that there are CMB fluctuations at a redshift of 1000. Okay. The location of where this bump should occur, the rough value for it, given the current cosmological model, was a prediction. Okay. And when you go to the galaxy observations, you can look at these galaxies, you can figure out what is the correlation function of these galaxies, and use the same standard ruler that you had observed at a redshift of 1000. You can use the same standard ruler at a redshift of, say, 0.3 or 0.2 and 0.55, right? So something which is much, much closer, and look at it in the galaxy distribution, the same scale you can observe in the galaxy distribution. And it has been observed so far. Okay. So this is data from the SDSS. You see, this is showing you the excess number of pairs that you have in the galaxies at a particular scale, okay, compared to if the galaxies were distributed in a completely random manner. Okay. So that is what is plotted here on the y-axis. And you see that it goes down, but instead of following just some kind of a power law, it has a deviation and a particular feature here. There is a bump here. This bump is coming from the same physics that the CMB is coming from. Okay. And so you can use it as a standard ruler. You can measure the angular diameter distances to these different redshifts at which these galaxies are located. Okay. And so you can use the BAOs now in order to also measure the cosmological parameters, right? So this is showing you omega matter, omega lambda. Supernovae went like this. The CMB was going like this. The BAOs, they go something like this. Okay. So everywhere, concordantly, these different observations, they rule out different kinds of parameter spaces and then tell you that our universe should be somewhere. Okay. The cosmological parameters that describe our universe should be somewhere around here, roughly 30% matter, 70% dark energy. You can also ask the question, if it is dark energy, what is its equation of state? Is it W equal to -1 or something else, right? And so that's what is shown here on this particular graph. Again, the supernovae tell you rule out different spaces, the BAO rule out different spaces, the CMB rule out different space. But in the end, you converge onto this value, which is W of -1, understandably with large errors, but we are trying to put constraints on this. Okay. So these are the geometric probes. In addition to these, there are also growth of structure probes, okay, where, for example, you can look at how the fluctuations in the initial stages in the early universe, how they grow as a function of time. Remember, this is a tussle between gravity, which is trying to increase these density fluctuations. So that's dark matter for you, right? Matter is trying to cause these fluctuations to grow from these initial tiny fluctuations to what you see today. But there is dark energy, which is trying to move the space apart, right? To increase the distance between each of these galaxies. And so it is acting against the fluctuations growing, right? So there is a tussle, a competition between dark matter and dark energy. So based on growth of structure measurements, you can also put constraints on what are the cosmological parameters of the universe. So this is something that is also done. So you can measure how galaxy clusters grow as a function of time, right? You can measure their abundances, and it can put constraints on the cosmological parameters. There's another thing called redshift space distortions. Again, something I have not gone into the details of, or nor I will get the time to go into. You may learn about it in the structure formation classes. The third thing that you can do is to look at the distribution of dark matter itself. Okay, so you can do a direct mapping of where matter is distributed in the universe using gravitational lensing. So this is particular part that I actually do research on actively. Okay, so this gravitational lensing thing is again a very, very interesting phenomena. It is related to the bending of light in the presence of matter. This is something that you can also learn about. We have given lectures on this. This year, we will not give you lectures on those. So I'm just going to point you to this particular discussion session, which we are going to have on Friday, 10 a.m. So what we are trying to tell you to do, and you should have received an email about this, is to go and look at these 3 different lectures that we delivered last year. And then we'll have a discussion session about it. So you can ask us questions about gravitational lensing, about the introductory parts, about strong lensing, about weak lensing. So all of these things are explained there. So please go ahead and look at it. But the important part that I want to tell you is using gravitational lensing, you can create maps of dark matter. And we have done this. This is some of the recent results that are presented in 2018, which I was part of, where we try to actually map out what the dark matter distribution looks like. We can make out a 3D map of the dark matter in a particular part of the universe. We can compare how structure is actually growing in the universe. So with this, I come to the end of this particular lecture. Okay, so we started the lectures with these big questions, right? We wanted to know how old is the universe. We wanted to know what it is made up of. We wanted to know how it came into existence and what is the fate of the universe. Right? So we have tried to I've tried to answer some of these questions, or at least try to give you the science behind how these questions can be answered. We have learned how old is the universe. We have learned to measure the Hubble constant. We have learned to measure the constituents of the universe, which governs the expansion. So I've told you what these formulas look like. I've told you the observations which you can use, the luminosity distances, the angular diameter distances as a function of redshift. And that is something that you can use in order to measure the geometry of the universe, the constituents of the universe. Right? So all of these things I tried to tell you. I also tried to tell you how things evolve from the earliest stages in the universe, right? From very, very early on, when the universe was extremely small, 10 to the minus 10 seconds or so, to today, right? I told you how you formed things in the earliest minutes, right? How you formed this helium, how you had the protons, right? What kind of interactions they underwent, right? All of these things, what were their number densities, how these number densities changed with time. What is the temperature of the photons that you expect? How can it be different from the temperatures of the neutrinos? All of these physics, right? We use the physics that we knew of the standard model today and general relativity, applied it to the very early universe to try to learn how the universe may have evolved. Right? So it's pretty cool what we can learn just based on what we have done in the observatories, and that is not just some figment of someone's imagination. It's not like a theorist just dreamt about this particular model and came up with this model that I've talked about, right? It is a model which indeed has some basis in theory, but it is also supported by numerous observations, right? So this is why it is so interesting, right? That we are actually living in this particular time and epoch, that we can actually learn about these things. We can learn about the universe, and we can learn about our own origins, right? And this is all being done in a scientific manner. You can ask, right? Are there pictures or are there things that we don't understand? Of course, there are many, many things that we don't understand, right? We don't understand exactly what dark matter is. We don't understand what dark energy is. But compared to what we were, say, 100 years ago, we have made tremendous progress, right? So this sphere of our ignorance, of our not understanding, keeps on receding, right? And I would want many of you as students to go ahead and take part in this big cosmological adventure, right? In order to make sure that our knowledge keeps on expanding, such that we can actually push the limits of our ignorance, of our things that we don't know, even further and further. Okay, so this is where I will end. I hope that was useful. It was a pleasure to give you these lectures. So let me try to look at some of the questions that I may have had. So sorry, it took a little bit more time than usual. I wanted to finish this. Okay, so these fundamental observers, what do you mean by fundamental observers? So fundamental observers are the observers which basically lie on these coordinates, right? Lie on these co-moving coordinates, where they experience exactly the same history for the universe as a function of time, and they see everything to be homogeneous. Okay, so those are the fundamental observers. The fact that we can consider ourselves a fundamental observer, that can be done only after you remove that peculiar velocity component. Okay, and so that is what is important in order to understand what this fundamental observer is. Okay. What is this? There is a particular pattern we see in the last plot, a disk with somewhat higher temperatures. What is the cause of the disk-like pattern? So I suppose you are talking about the CMB pattern. Or maybe you're talking about this particular disk. Right. So this particular disk that you're talking about, that actually is the Milky Way. Okay. So the Milky Way also emits in the microwave, and this is because of the dust within the Milky Way. So that emits in the microwave. And so this particular galactic plane is something that you need to remove before you start to see the cosmological fluctuations. Okay, so that disk was not removed in this particular plot, but in the next plot, what you are seeing is that particular disk being removed. So the way you remove it is because it is dust, we understand roughly what is the thermal spectrum of the dust. And so if you have measurements of the temperature at different frequencies, then you can try to get rid of the dust contamination at those locations. So the error bars are also large at the temperature fluctuations at this particular disk location. But that is all accounted for when you do all these analyses. Okay. Oh, someone had answered it already. Yeah, good. Let's see. Can the cosmic microwave background help us in understanding the real size or the dimension of our universe as a whole? Yeah, so if you understand what are the constituents of the universe, then you can use the constituents of the universe to figure out what is the horizon, right? What is our observable universe, right? What is the furthest that photons have come from to us, and we can still see them, right? Because things which are even further away, they have not had the time to reach us. So if you have the cosmological model, then you can figure out what is the horizon. So all these observations, the cosmic microwave background, it allows you to pinpoint what this cosmological model is. Okay, so then it allows you to figure out what the horizon is, and that is what is called the observable size of the universe. Right? In fact, the observable size will be limited in terms of the photons, right, to the location where the CMB comes from, because before that, there's a big fog, right? So you cannot see through the CMB using photons. You can see through the CMB maybe using neutrinos, right? Because the neutrinos have stopped interacting after they decouple, right? So then you can go back to the neutrino epoch. You can also peer even further in if you can observe the primordial gravitational wave signal, for example. This is something that also leaves some imprints on the cosmic microwave background polarization signal. Okay. So again, I don't have time to go into the details of that, nor am I an expert in it, right? But if you observe those primordial gravitational waves in the CMB polarization signal, then you can peer even further in to the epoch of like inflation, for example. Why is the CMB always shown in an ellipse? That is nothing but a projection. You can show it on a sphere as well. It doesn't matter, right? So it's just like asking, okay, why do I take the map of the world and I show it in a rectangular pattern? So it's just one particular projection that helps out. Okay, in the angular distribution, how do you decide the location of points and distances from the point subtending those angles, right? Yeah, so these particular angles, I believe. So you actually average over all points. Okay, so you go to this point, then consider all the points which are at an angle theta away from this. Then you go to this point, again do that, and then you calculate the average. Okay, so you go to each and every point in this map. You don't go to just a few points in the map and then calculate that average. You go to each and every point. So that gives you one value of C of theta at one angular separation, right? Once you do that average, then you change that angle. You go to a larger angle and calculate again this C of theta. Another angle, calculate C of theta. When you take the Fourier transform or this spherical harmonic equivalent of it, you get this CL. That CL is what is shown in this post. Okay, so I hope that helps, right? So this corresponds to each and every different angle, right? So this is smallest angles, and these are the largest angles. Okay, so I hope that helps. Oh, there are more questions. How CMB will change over large period of time? I mean, is it truly constant background radiation or actually evolves over large time scales? Of course, over large time scales, it does evolve, right? So today, you are seeing it at a temperature of 2.73 Kelvin. If the universe expands by a factor of 2, you will see that the temperature will have dropped for this CMB, right? So that's what you will observe. It will be observed at a even lower temperature if you go to a future time scale when the universe has grown bigger. Okay. Of course, in the same time scale, photons from even further out would have come and reached you, right? So right now you see the fluctuations which are just rightly timed when the CMB recombination happened, and those photons are reaching you right now. Right? That's the perfect timing for the moment. So those are the fluctuations that you see today. But if you go to in the future, right, when the scale factor is say factor 2 larger than what it is, then you will be seeing the photons coming from a different location and reaching, right? So those temperature fluctuations will be slightly different compared to what you see today, for example. Okay, so that's expected. my interest is to know about some textbooks. Again, yeah, please take a look at the website. I do give links to certain lecture notes and certain textbooks which cover many of these physics and many of the things that I've talked about. So please go to the website and take a look. In fact, one of the things that I will recommend is Jayant Naraykar's textbook, Introduction to Cosmology. It is very well written. It is understandable at the undergraduate level as well. So please take a look. It has chapters on GR as well and then cosmology. So it's pretty much self-contained. It's an old book. So if you want to learn more about like actually do calculations and so on, then there are books by Scott Dodelson, for example, Frank van den Bosch, Simon White, and Ho Jun Mo. It is a book on galaxy formation, but it also has many of these cosmology components. So please take a look. There are a number of things that you can find. I have links included to them on my website. So just go through it. Okay. Surajit, CMB is all right. Yeah, ellipse is fine. Will the CMB temperature decrease in future? Yes, it will. You also have to remember that the photons that you see today, right? Those come from some very, very different part of the universe, right? So it comes from some kind of a sphere around us, which is exactly at the right distance, right? So that the photons which were released at that particular point of time at the recombination, they come unhindered towards us, right? So similarly, the photons which were released at our location, they would be reaching at the same location there, right? Just because of the reversibility argument, right? And so if there are some intelligent beings who are present there, they will not see the Earth right now. They will be seeing the CMB as it was released from our location. But the CMB radiation, which was at our location, it is not trapped here, right? It got dispersed. Okay? But at the same time, the CMB, which was released at on a sphere, it has come to us. Okay, so there's this reversibility argument. Can we associate a temperature to the cosmic neutrino background? Yes, and if you associate a temperature, it will be roughly this 4/11 raised to 1/3. Right? That's the factor that we derived by these degeneracy counting arguments. Okay, I think the future as well receive CMB, will it overcome temperature decrease due to the expanding universe? Yeah, so the temperature of the photons, it always increases as the scale factor of the universe. It's like 1/A, right? And so it perfectly compensates and still it remains a black body. And so you will still see that it will have a black body spectrum, but with a temperature which is slightly low. Okay. So it's not like it will, the temperature will decrease in the proportion which is exactly equivalent, which will be given if the lambda increases by this scale factor. Okay, so it's exactly the same amount by which the temperature will increase. Okay, good. I think we have had a lot of questions. It's almost 12:50, right? So maybe I can stop here. If you have more questions, put it in the Google form and I will try to respond to them in a Google Doc. I have not responded to all of the questions in this Google forms yet because many of them were things that we already covered either in the next lecture or something like that. Right? So, okay, I hope I have given you a brief outline of cosmology and that it helps you to understand the next set of lectures that come up. Okay. Thank you so much. Bye-bye. Sagar? I suppose I can leave now, right, Sagar?